Good morning. Hello. Anybody has joined?
Good morning, sir.
How many students have joined?
There are around 11.
Yes.
11.
11 students. See, as per the earlier notice, once they decided that the test will be offline, then online. Okay. So now most likely everything is on online. Okay. Except few students, all has opted for online, right? So from the operation research, so most likely it is online. If anybody is interested for the offline, so he has to write me or he has to contact me whether he is interested for offline or not. Okay. Otherwise, by default, it is online. Okay. So I am going to take a test, the online test. So most likely all 11th or 12th. 11th is Monday, 12th is Tuesday. Okay. Is it all right? So please note down, and this slot it is fixed, because once this is fixed, then I have to plan accordingly to prepare this question paper and talk to the administrator who will conduct the test. Okay, is it all right? 11th April is all right? I'll write mail to everybody. Okay, so today after the class I will write mail to everybody. So and see, the test this time will be for 1 hour, right? Not for half an hour, it is 1 hour. Because, due to yes, no type, I was planning to conduct the, second test on March 15th. So, but in the meantime, I got a notice that the test will be offline. So you send the question paper. We have sent the question paper. Again, they have returned back the question paper. Okay. So then they are saying it is online. Now they are saying you ask the students. So you based on their option. So most likely, I think all you are opting for online. Yes or no? Are you able to hear?
Yes, sir.
Okay. So please inform everybody it is online. If anybody is interested for offline, so you see the question paper what we have sent. So same question paper I have to use. Okay. So I have not opened. So same question paper I will use. Okay. So if it is offline, it will be 2 hours. Okay. And if it is online, it is 1 hour. Okay. For online, I have not shared the question paper. I will share the question paper. Okay. So because this is the end semester, generally end semester for 2 hours, and this online test either on 11th or 12th, most likely on 11th. 11th we have 2 hours. Okay, 8 to 9, 9 to 10. Okay, so based on the availability, so we will utilize the time. Okay, if say that 8 to 9 is free, then 8 to 9 or maybe 9 to 10. Okay, is it all right? Please inform all your friends. So I will also send mail because some are not attending the class and also they are not interacting. So very difficult to know. And now everything is final. The test will be online. Okay, most likely online for all. Okay, if anybody is interested for offline. Okay, but two things you cannot. Okay, so two things cannot be, because see, first I will take the online test. So then offline, not that. Okay, based on your decision. So if you online, so it is online for all. If it is offline, so okay, generally offline, most likely few students are opting. So there is all right. I'll conduct accordingly. Okay, the offline will be 2 hours. The question paper already ready. It is for 2 hours. The online is 1 hour. Okay, and online the way you appeared the test same way. Okay, so this time I am giving more time because so that you can find enough time to compute your answer. Okay, is it all right?
And sir, what about the number of questions, sir?
See, number of 1 hour means, see, if it is see, for half an hour you are answering, say, then number of questions will be little more. Okay, right? Maybe 5 questions. 5 is okay.
Oh, sir.
So you are getting, say, nearly 12 minutes each. Okay, for each question. Okay, so not 3 questions. Okay, then 3 questions will be okay. So and 5 question I think is okay. So that also objective type. Okay, so and I have only taken one test. Okay, and some components are marked because you're writing code or the other things. Okay, another component is there, and this is the final one, the online test for 1 hour. Okay, so if anybody has some problem, specific problem about the test timing or date, so what I have mentioned, please he should inform me. Okay, so otherwise on 11th April is the final day for to take the test. Okay, so I have to talk to the administrator to prepare accordingly to take the test. Okay, so we are discussing in the last class about the game theory. Most likely we are just discussing about the 2-person zero-sum game. Okay, 2-person zero-sum game in the sense, say 2 players are involved. 2 players are involved for a matrix game. So 2 players are 2 groups. So and here we are saying zero-sum game in the sense, since 2 players, whatever the player 1 is gaining, so same amount it is a loss to the player 2. Okay, so if it is gaining 10 units, so the loss is there for 10 units. So plus 10 minus 10 altogether it is 0. So we are saying zero-sum game. If player B is winning, then player A is losing. Okay, so here the game we are representing in terms of a payoff matrix, a matrix of size m by n. The payoff in the sense, so what the player 1 is paying to player B or player B is paying to player 1, payoff. So the elements of the matrix are the payoff. So there are m into n number of elements. So the player A, namely, he has strategy like say A1, A2, AM. These are the strategy. Generally, they are the pure strategy. Pure means, so he can use strategy 1 or 2 or M. And similarly, player B has strategy B1, B2, Bn. Okay, so there are n number of strategy. He can use strategy 1 or 2 or 3 or up to n. Pure in the sense there is no chance, no probability. Once probability is involved, by probability he is not sure which one he is going to utilize, whether B1 or B2 or Bn. So let me say the chance. So chance, something like the chance of using first strategy, the chance. So the B1 may be half and B2 may be 1/3, maybe B3, etc. Okay, so these are the chance, and sum of the chance, sum of the probability of using strategy B1 plus sum of the probability of chance using strategy B2, etc. up to Bn, the probability, this probability equal to 1. If one strategy he is not using, chance is equal to 0. The probability is 0. So here, once chance are involved, it is called pure strategy. If chance is not involved, if chance are involved, then it is a mixed strategy. If chance are not involved, it is pure strategy, pure or mixed. Okay, so we are discussing earlier about the pure strategy. So this is the payoff matrix. payoff matrix of a zero-sum game. So with respect to payoff matrix, we mention here A1, A2 up to AM are the strategy of the player A. These are the pure strategy. And similarly, B1, B2, Bn are the strategy of the player B. These are called also pure strategy for the player B. And Aij is the payoff to player A by player B when player A selects his strategy AI and player B selects his strategy Bj. This Aij is positive means A receives from B, negative means B receives from A. Okay, if it is 0, there is no gain for anybody. If it is 0, so there are m into n number of elements. Okay, so with respect to m into n number of elements, so the payoff matrix has size, so m by n. So individually Aij is the element of the matrix, ith row, jth column elements. If it is positive, then it is a gain for player A. If it is negative, it is gain for player B. Whatever the player A is gaining, that is from B, and whatever B is gaining, that is from A. If it is positive, it is for the player A, gain is for the player A. If it is negative, the gain is for the player B. If it is 0, there is no gain. Okay, so now we are talking about a 2 by 2 matrix, payoff size 2 by 2. The player A has two strategy, pure strategy A1, A2, and player B has two pure strategy B1, B2, and these are the elements. If and see, all the elements are positive. All the elements are positive means it is a gain for, always there is a gain for player A. So there is no gain for player B. Now, what is the intention of player A? The player A, his desire is to maximize his gain. And what is the desire of the player B? His desire is to minimize his loss. Okay, one is interested to maximize his gain, other is interested to minimize his loss. These are the elements. Now, so whether we want to check whether it is a stable game or unstable game. How do we check whether the game is stable or unstable? We check in this manner. Say row wise, the first row there are two elements 4 and 5. So we find the minimum of the first row elements. Minimum. So why it is so? See, the player A is selecting his first strategy. Once he is selecting his first strategy, so what is the options for the player B? He may select strategy 1 or strategy 2. Okay, if he is selecting strategy 2, then he is losing 5 units. So if he is selecting strategy 1, he is losing 4 units. So suddenly, so B's desire is to minimize. So this is ideal. So ideal in the sense 4 and 5. So the minimum is 4. Similarly, if the player A selects his second strategy, B has option. Either he has to use strategy 1 or strategy 2. So if he is using strategy 1, then he is losing 2 units. If he is using strategy 2, he is losing 3 units. The minimum is 2. So it is ideal he has to use the strategy 1. Now, row wise we find the minimum 4 and 5, minimum is 4. Second row minimum 2, 3, minimum is 2. out of 4 and 2, we select the maximum. This maximum is becoming 4. So maximum is becoming 4. So now, similarly, we'll talk about the player B. He is selecting, say, strategy 1. So B has 2 options. So A has 2 options, 1 and 2. So similarly, what do we do? We find the maximum of first column elements. Similarly, maximum of second column elements. The maximum of first column elements 4, 2. Maximum is 4. Maximum of second column elements 5, 3. Maximum is 5. Then we find the minimum. First we take the minimum, then maximum. So we say it is max min, and here it is minimax. Say first max, then min, so minimax. So we find this 4 is same. Max min and minimax value is same. So this 4 is a saddle point. So this game is a stable game. So this table we can also find from the dominance rule. Dominance rule. How do you find the dominance rule here? So you see the first column, first row 4, 5, second row 2, 3. First row is dominating second row. First row is dominating second row. So we can drop second row. 4, 5. 4 is more than 2. 5 is more than 3. So for player A, bigger elements are better. So 4, 5 is dominating 2, 3. So we drop second row. Only one row is there, 4, 5, and 2 column. Column elements are 4 and 5. Now 4 and 5, see, since B has 2 options, column 1 and column 2, B will exercise his first option, first strategy. So B is interested to minimize his loss. So 5, 4. So minimum elements are better. So 4 is the elements. The minimum is 4. So here this game has a saddle point. The saddle point is nothing but the value of the game. Value of the game equal to 4. Once I am saying it is 4, the player A is gaining 4 units from the player B. The player A is gaining 4 units from the player B. And once it is a gain, so the same 4 units, so B is losing. Okay, B is losing. So that is a zero-sum game. The value of the game equal to 4. And the optimal strategy. What is optimal here? A must use strategy 1. B must use strategy 1 also. Okay, it has only one saddle point and the value of the game equal to 4. Okay, is all right? Hello? How many students are available now?
Yes, sir.
How many students are available? 30? How many? Please tell me.
Sir, 43 are available.
Okay, all right, good. Okay, so now I'm going to the second problem. Second problem, here also the player A has 2 strategies, strategy 1 and strategy 2. This player B has also 2 strategies, strategy 1 and strategy 2. Here all the elements, you know, some are positive, some are negative. There are 4 elements. 2 are positive and 2 are negative. 2 are positive and 2 are negative. With respect to this, so we are checking whether the game is stable or unstable game. Now the question is, how do we check? How do we check the game is stable or unstable? The rule is like this. The rule is like this. Say, with respect to first row elements, 2 and 3, 2 and minus 3, we find the minimum. Minimum of 2 and -3 is -3. And second row, there are two elements, -3 and 4. And minimum is also -3. So first row minimum is -3. Second row minimum is -3 also. So we are looking for the maximum of -3, -3, the same as -3. So first you have taken minimum, then maximum. That is max min. This max min element is -3. The max min element is -3. Okay. Now we are checking about the column. Column maximum. First column 2 and -3. What is the maximum? Maximum is -2. Maximum is 2. Then second column -3 and 4. What is the maximum? What is the maximum? Maximum is 4. So after taking the maximum, we are taking the minimum. That is minimax. Earlier you have taken so max min, then it is minimax. So 2 and 4. First column maximum is 2. Second column maximum is 4. So we find here. So among 2 and 4, we are looking for the minimum. Minimum is 2. Earlier, what you have got? The max min value is -3. Here, minimax value is 2. -3 and 2, they are not equal. So since they are not equal, the game is unstable. If they are equal, then the game is stable. So once it is unstable, we cannot find the value of the game. So the pure strategy are no longer applicable. Here we have to use the max. So mixed strategy. Mixed strategy in the sense. So what is the chance of using first strategy for the player 1? What is the chance of using second strategy for the player 1? So we have to calculate. And similarly, what is the chance of using first strategy for player B? And what is the chance of using second strategy for player B? So this chance, since it is mixed, the chance cannot be 1 or 0, something like it is mixed. So maybe half, maybe 1/3, 2/3, maybe 3/4, 1/4, etc. Okay. Sum of these two strategy. Okay. So sum of the probability of two strategy equal to 1. Okay. So this is a unstable game. So we like to know here in this problem, not the value of the game. We are interested to know what is the expected value of the game. So some probability is involved. So once the probability is involved, we are interested to find the expected value of the game. Expected value means expected gain for the player A or expected loss for the player B. So we are interested to find out. So we'll find out after some time, okay, for this problem, once we know the method. Okay. A primary objective of game theory is to develop rational criteria for selecting the strategy, their individual strategy for the first player and strategy for the second player. Okay. So now another problem, find the optimal solution of the two-person zero-sum game. Determine the saddle point solution and the associated pure strategy and the value of the game. So this is possible once the payoff matrix is given. Once the payoff matrix is given. Payoff matrix. So this is another problem. This player A has three strategies. A1, A2, A3. These are three strategies for the player A. The player B has four strategies, B1, B2, B3, B4. So there are two players. Generally, as I mentioned earlier, generally rows for the first player, columns for the second player. So we may interchange also, but if you will interchange, we will also select the similar criteria. Generally, rows are for the player 1 and column for the player 2. Now, here also in the pair matrix, there are 3 into 4, altogether 12 elements. 12 elements, all are real number. Here also we find all the elements are also positive. So also positive means it is a gain for the player A. Now we are looking for gain. Suddenly, how much gain? So B is trying to minimize his loss. Okay. So how to find? How to solve the problem? We take the row wise minimum. First row, there are 4 elements, 8, 6, 2, 8. Minimum is 2. Second row, there are 4 elements, 8, 9, 4, 5. 8, 9, 4, 5. There are 4 elements, minimum is 4. Third row, 7, 5, 3, 5. Minimum is 3. Among these 3 minimum, row minimum, we find the maximum value. So after finding the maximum value, that value we are naming as max min. First minimum, then maximum. So it is known as max min. 2, 4, 3. 2, 4, 3. What is the maximum? Maximum is 4. 2, 4, 3. Maximum is 4. Now, similarly, we take the maximum of first column. 8, 8, 7. So maximum is 8. Then second column, 6, 9, 5. Maximum is 9. Third column, 2, 4, 3. Maximum is 4. Fourth column, 8, 5, 5. Maximum is 8. After finding the column maximum, we take the minimum. That value is known as minimax. Earlier we got max min. Max min is 4. Here we find the minimax. First maximum, then minimum. That is also 4. So both are equal. Since both are equal, the game is a stable one. Once it is a stable one, so whatever there is equal value, max min and minimax both are same. This is the value of the game. Value of the game equal to 4. If it is 4, what is the optimal strategy? Player A using his second strategy, player B using the third strategy. As a result, B is losing 4 units. That is, he is trying to minimize his loss. So, but he has lost only 4 units. Okay. So the value of the game equal to 4. 4 is positive. So this is a gain for the player A. And this 4, B is losing. So that is a loss for player B. So it is a zero sum game. The value of the game equal to 4. And optimal strategy equal to A2 and B3. A2, player A is selecting his second strategy. Player B is selecting the third strategy. Okay, this is the value of the game. Is it all right? Hello? Do you have any doubt here in this problem? Hello?
No doubt, sir. Clear, sir.
No doubt. Okay. Next. The solution of the game is based on the principle of securing the best of the worst for each player. If the player A selects his first strategy, then whatever the player B selects, A will get at least 2. You can see here. Okay. So that is the reason we are writing 2. And similarly, other rows. And we have explained everything. So for this problem, the value of the game equal to 4. This we are naming as the value of the game as new. This new is the value of the game. And this 4, whatever you obtained, is called the saddle point. Why saddle point? This game has 12 elements. 12 elements. 3 rows, 4 columns. 12 elements. One of the element you can see here 4. The game has only one saddle point, that is 4, and that is the value of the game. Okay, and it's just stable game. Okay. I have already mentioned this type of problem. This type of problem we can solve using method of dominance. Method of dominance. So you can see here the same problem. If you are using method of dominance, how do we check? So here you can see there are 3 rows for the player A, 8, 6, 2, 8, the first row elements. Second row elements, 8, 9, 4, 5. 8, 9, 4, 5. This third row elements, 7, 5, 3, 5. If you are using method of dominance, say how can you use? You can see here 8, 9, 4, 5, 7, 5, 3, 5. Please compare A2 and A3, second row and third row. Second row, third row. The second row elements 8, 9, 4, 5. Third row element 7, 5, 3, 5. So we are comparing 8 and 7, 8 is better. 9 and 5, 9 is better. 4 and 3, 4 is better. 5 and 5, similar. So now if you compare these 3, 8, 9, 4, 7, 5, 3, 8, 9, 3 is better. So 7, 5, 3, the lesser value. A is interested to maximize his gain. So A2 is dominating. A2 means second row is dominating third row. Second row is dominating third row. So using the principle of dominance, the third row can be deleted. Third row can be deleted from the problem. So if you delete third row, so this problem has simply there are 2 rows and 4 columns. 2 rows and 4 columns. We are deleting. You can see here, after deleting, we have here 2 rows and 4 columns. Now another thing. So you cannot now compare between first row and second row. 8 and 8, both are same value. 6 and 9, 9 is better. 2 and 4, 2 and 4, 4 is better. 8 and 5, 8 is better. So this A1, A2 cannot be compared. A1, A2 cannot be compared because so 8, 6, 2, 8, 8, 9, 4, 5. Okay, due to the last column elements 8 and 5, other 3, the second row elements are better. But 5, 8 and 5, so 8 is better. So these 2 rows cannot be compared. Now we are coming to the column. For the player B, the column elements which has lesser value, it is better. The column elements, columns are for the player B. The elements which has lesser value, it is better. So if you compare 2 and 4, 8 and 5, 2 and 4 are better than 8 and 5. Better in the sense they are lesser. So lesser is better. So B3 and B4. B3 is dominating B4. we can drop B4. Similarly, 2, 4 and 6, 9. So 2, 4 dominating 6, 9. We can drop second column 8, 8. Okay, and B3, B1, B2, B1, B3. So 2, 4 is also means B3 is dominating B1. We can drop B1. So in this matrix, the remaining matrix, there are 4 column and 2 row. 3 columns we can delete. We can delete first column. We can delete second column. We can delete the last column. As a result, so our payoff matrix has only 2 rows and 1 column. If you compare 2 and 4, if you compare 2 and 4, 4 is better. Okay. If you compare 2 and 4, 4 is better. So B has no option. B has no option. Okay. Only one option. But A has option. A and A1 and A2. So if player B3, player B is selecting his third strategy, so this player A, he may select either strategy 1 or strategy 2. So for his maximum gain, he has to use second strategy. So here 4 is becoming the value of the game, and this 4 is also becoming the saddle point, and we have solved the problem using method of dominance. 2 ways we have solved, and this is possible because the game is a stable game. If it is unstable, this method of dominance cannot be applied directly. We have to apply indirectly. That also we'll discuss. Okay. The second problem, there is a question. See, this is a payoff matrix. So in this payoff matrix, it is given the elements are some real number, also some constants is given, something like P and Q. We are interested to know what has to be the value of the elements P and Q, so that there is an element, the game has a saddle point. The game has a saddle point means this is a stable game. This stable game. So for this stable game, we are interested to know what is the value of P and Q. So this payoff matrix has 3 rows and 3 columns, 2 players, as you know. So A and B, A has 3 strategy, B has 3 strategy. So the elements are like this: 1, Q, 6. So we are taking the row wise minimum. So once we are taking the minimum, so in the first row, minimum value is becoming minimum of 1 and Q, because Q is unknown. So Q is unknown. So we are leaving 6 because 6 is more. So one of them, Q and 1 and Q. So now we do not know what is the value of the Q. So we are keeping the minimum is 1 and Q. So minimum is minimum of 1 and Q, the first row. Second row elements, that is P, 5, 10. So minimum if you take, then minimum value is coming P and 5, 10 we are leaving. So then third row elements, 6, 2, 3, minimum is 2. So the row wise, you see, we are taking the minimum, then maximum. So we are interested to know what is the max min value. What is the max min value? So that this elements 2, 2 is becoming our saddle point. Now we are interested to take the column maximum 1, P6. This maximum of P and 6, that is the first column maximum. Then maximum of Q and 5, that is the second column maximum. And 6, 10, 3, the 10 is the third column maximum. Say it is given already the elements, second row, second column elements, the element 2, 2 is our saddle point. This is equal, actually our saddle point equal to 5. It is given. So with respect to 5, so now we are interested to know, say, what is the value of P and Q so that this 2, 2 is becoming our saddle point. Now, if I'm talking about, say, P and Q, let us say P and Q both are 5. P and Q both are 5. Okay. P and Q both are 5. If both are 5, what is happening? So 5. So then maximum value is becoming 5. And here minimum value is also becoming, if I'm saying, so P equal to 5, then it is fulfilled. Okay. So here both must be satisfied. P must be greater than or equal to 5 and Q must be less than or equal to 5. Select, let me say, so P is greater than or equal to 5, Q is less than or equal to 5. Let me say a value P equal to 6 fulfilled, Q equal to 4, P equal to 6 and Q equal to 4. So on value I am selecting P equal to 6. If I am saying P equal to 6, what will happen to this value? And Q equal to 4. P equal to 6, Q equal to 4. Okay. So P greater than or equal to 5, I'm saying it is 6. So a 1 and Q. So minimum of Q, so minimum of 1 and Q equal to 3, Q equal to 4. So 1 and 4, minimum is 1. So minimum of 6 and 5. 6 and 5. So P I'm selecting 6 and Q I'm taking 4. So earlier it is becoming minimum is 1, here it is 5. So as a result, maximum equal to 5. And similarly, so if you take P equal to 6. So this value is becoming 6 and Q equal to 4, maximum of 4 and 5. Maximum of 4 and 5 equal to 5. So we'll find ultimately 5. So this is fulfilled. So this is fulfilled for such value. P has to be greater than or equal to 5. Q has to be less than or equal to 5. Then it is fulfilled. So the answer is P has to be P lower bound is 5. Upper bound can be anything. And the Q upper bound is 5. Lower bound can be anything. So that it is fulfilled. So with this restriction, we have got the value of the saddle point. The saddle point equal to 5. Okay, this another problem. Specify in this problem, we are interested to specify the range. Specify the range of the value of the game. Say, with respect to the first row elements, 3, 6, 1, minimum is 1. Second row elements 5, 2, 3 in this problem, minimum is 2. And second row elements 4, 2, 4, minimum is 2. Among 1, 2, 2, the maximum is 2. Maximum is 2. And if you are talking about the column maximum, the first column maximum value is 5. Second column maximum value is 6. Third column maximum value is 4. So after finding this, we are finding the minimum. Minimum is 4. This one, what we are saying, the max min value is 2 and minimax value is 4. They are not equal. So the game is a unstable game. Okay. So if it is a unstable game, we are interested to know what is the the game has no saddle point. Say, what is the value of the game? So, see, 4 less than, this 4 is greater than 2. This minimax, first maximum, then minimum, that is becoming 4, then first minimum, then maximum, that is 2. So 2 and see, the 4 is less than 2. 4 is less than 2. So now the question is, what is the value of the game? So see, the answer is the value of the game lies between 2 and 3. So 2 and 3. Why 2 and 3? So the reason is both the player must use random mixes of their strategy so that A will have maximum. A will maximize his minimum expected return and B will minimize his maximum expected loss. So please note down. So what is the A's intention? A's intention is to maximize his maximum expected return. Okay, that is the gain. Maximize his minimum expected return. And B's intention is to minimize his maximum expected loss. So B is losing something. So whatever he is losing, he is interested to minimize that. And A's intention is to maximize his minimum expected return. So here, since it is an unstable game, we are interested to find the expected value of the game. Expected value of the game. The value of the game lies between 2 and 3. So 2 and 3. Actually, it has to be 2 and not 2 and 3. It has to be 2 and 4. Okay, 2 and 4 in this range. So we are in not. So certainly 2 cannot be. Say 2 and 4. 2 cannot be and 4 cannot be in between. So it is. So it is less than 4, greater than 2. Less than 4, greater than 2. So 4 cannot be, 2 cannot be. In between this 2 and 4. So this is less than 2, less than 4 and greater than 2. Okay. This problem already have in the last class we have say discussed. Again I am repeating. So how to find the minimax then max min. So minimax and max min. Say how to establish this so that in a matrix game that is maximize over I, first minimize over j, aij, then maximize over I. Okay, so this quantity minimize then maximize, that value is less than equal to first maximize over I, then minimize over j. So this value, the right hand side is always greater than or equal to the left hand side. So minimax value is always greater than or equal to max min value. So if they are equal, then the game is stable. If they are not equal, the game is unstable. So here, with respect to this assumption, let us assume the Ri, the ith row elements, the Ri, the ith row elements, its minimum value, consider the ith row elements, then you take the minimum value over j. So this is becoming Ri. That Ri we maximize further. We maximize further. So over I, this is becoming R. Okay, the left hand side is becoming R. And similarly, the right hand side. So let's Cj, that is the jth column elements. If you want to maximize over I, of Aij. This is Cj, and after maximizing, then take the minimum over j, Cj, that is C. So we have here something like Aij less than equal to Cj and greater than equal to Ri. So we have introduced Aij in between here. Aij less than equal to Cj, greater than equal to Ri. Therefore, with respect to this relationship, we can write always maximize Ri is less than equal to Cj for all j, and also you can write here. So once you maximize this and minimize Cj, the maximize Ri less than equal to minimize Cj. This you can write R is less than equal to C. The C value always greater than equal to R. So if they are equal, then the game is stable. If they are not equal, the game is unstable. So now, with respect to this, we are going to discuss how to solve a matrix game where the elements has no saddle point. There is no saddle point, and the game is an unstable game. How to solve such game? So whenever we find the game has no saddle point, so we use probability distribution over his set of strategy. Mathematically speaking, we are introducing some probability distribution. Let's say xi equal to probability that the player A will use his strategy ai, I equal to 1, 2 up to m. There are m number of strategy. So here we have something like x1 plus x2 plus x3 up to xm. This equal to 1 because it is using distribution over his strategy. The sum of the probability equal to 1. Individually, x1, x2 up to xm, they are non-negative. This condition sometimes you are using in the linear programming. All the variables are non-negative. Here the probabilities are non-negative. And what is the extra condition? Sum of the probability equal to 1. Sum of the probability equal to 1. Okay. So please note down. So x1 plus x2 up to xm, their sum equal to 1. Since their probability, they are all non-negative. Can be 0, can be positive. No question of negative. Similarly, yj. What is yj? Yj equal to probability that the player B use his strategy bj, j equal to 1 to n, and here also y1 plus y2 up to yn, their sum equal to 1, and this y1, y2 up to yn, they are non-negative. They are also probability. So here in this problem, something like if x1, x2 up to xm, they are the probability of using strategy a1, a2, am. Similarly, we have y1, y2 up to yn. They are the strategy probability of using strategy b1, b2, bn. They are also non-negative. In this context, the minimax criteria says that a given player should select his mixed strategy that minimizes the maximum expected loss to himself, or equivalently that maximizes the minimum expected gain. See, one is interested for maximizing his minimum expected gain. Other is interested for minimizing his maximum expected loss. How much he is expected to lose, that he is interested to minimize. And this next one you see here, maximize the minimum expected gain. maximize the minimum expected gain, and other one, minimize the maximum expected loss. These two criteria we have to use if the game is unstable. Okay. So see, if the player B is select his first strategy, player B is selecting his first strategy, that is B1. Now A has option, he has to use either strategy 1 or 2 or 3 or up to strategy M. These are the strategy he has to use. So now we are interested to calculate the expected payoff. What is the expected payoff? The expected payoff can be calculated in this manner. This AI1, see, why I1? Because the player B is selecting his first strategy. So AI1 into XI. I varies from 1 to M. Okay. If player A selecting his first strategy, some payoff, second strategy, some payoff, and similarly last strategy, XM, some payoff. So here we are finding the expected payoff. Expected payoff. Similarly, if the player B is selecting his second strategy, what is the expected payoff for the player A? That is summation over I varies from 1 to M, AI2. With respect to first strategy, we have AI1. With respect to second strategy, we have AI2, I2 into XI, this. So whatever in the left, right hand side, you are saying this value, that is known as expected payoff. Expected payoff. Okay. So this expected value, since they are all discrete variable, these random variables are discrete. So we have here, from the statistics, we know to find the expected value. So we find here the probability distribution, x1, x2 up to xm. So into the value, random variables taking value I. So x1 is taking value something like, so 1 1 1 2. Okay. So 1 1 2 1 3 1, etc. So AI1 into XI. Okay, this, and here AI2 into XI. Okay. So for the second strategy, if B is using, and if he's using the last strategy, BN, then the expected payoff equal to AI1 into summation over I varies from 1 to M, AIN into XI. Why IN? Because B is using the nth strategy. In this manner, we calculate the expected payoff. This is all right? Or any doubt? Hello? Hello? Are available or left?
Yes, sir. Yes.
We are calculating the expected payoff. Now, so the question is, we are going to solve the problem. So this is the expected payoff. So this payoff, so from whom? Because once the player B, he selected a strategy. So first strategy, this is the expected payoff. Second strategy, this is the expected payoff. So why expected value we have considered? The reason is the game is unstable. The game is unstable. So for the unstable, we are using some probability distribution. So we have got the expected payoff, this payoff from B to A. From B to A, because B has already played his first strategy, this is the expected payoff. Second strategy, this is the expected payoff. And the last strategy, this is the expected payoff. Okay. Now, what is happening to this? So as we know, the problem formulation is like this. So whatever the payoff, this payoff, so we are interested to know, so what is the minimum gain? What is the minimum gain? And that gain we are interested to maximize. So after the expected payoff is known, so we are finding the minimum. That minimum we are going to maximize. I'm repeating again. After finding the expected value, so how many elements? There are n number of strategy. So n elements. So these elements, as you know, we are writing I varies from 1 to m, ai1 into xi. First element. Second element, I summation over I varies from 1 to m, ai2 into xi. And the last one, I varies from 1 to m, ain into xi. There are n such elements. So we find the minimum. That minimum we like to maximize. That minimum we like to maximize. What is the extra condition we have imposed? The extra condition is like this. The extra condition is sum of the probability equal to 1. x1 plus x2 up to xm. These are the probability. Their sum equal to 1. And what is the condition? Since the probabilities are non-negative, the xi are non-negative. Okay, this is for what? This is for player A's problem. The player A has a problem. Similarly, we have a problem for player B. So how to establish this? This is you are finding player A's expected payoff. This player A has an expected payoff. Similarly, this player B has an expected payoff. So in this manner, so if the first player A is selecting his strategy A1, we have an expected payoff. What we are finding, this may be gain or loss. So that once A has played a strategy, first strategy A1, then we have some expected payoff for the player B. Similarly, A2, if he is selecting strategy A2, there is an expected payoff for the second strategy. And similarly, so if he is using the last strategy, that is AM, we have an expected payoff. That is given here. That is summation over j varies from 1 to n, a1j yj, summation over j varies from 1 to n, a2j yj, and summation over j varies from 1 to n, amj yj. This. And here, this problem is slightly different. What is that? We are taking the maximum. So earlier, same thing we have done. Row wise, if you think, we have taken the minimum, then we maximize for the player A, row wise. So here we are taking the maximum, then we minimize. Max min. So we say here max min, first minimum, then maximum, max min. Then here minimax, first maximize, then minimize. Okay. So this says the second problem, we want to minimize the maximum value of this. Okay. So where y1, y2 up to yn equal to 1, and this y1, y2 up to yn, they are non-negative. So very simple manner it is written, but it has some complicated expression. So complicated expression in the sense, how do we simplify? Okay. So there is a different problem. I'm not going to discuss that. I'm coming to the same linear programming problem. Okay, this. See, say the solution by linear programming method. We are talking about that. So if you see the problem here, there are two problems, age problem and beige problem. So player age problem is like this. Maxima is, that is the minimum value of the expected value of, there are, you know, n number of column for the player B. So with respect to n number of columns, so minimize the expected value with respect to first column and with respect to second column and with respect to the nth column. Okay, this, there are n such columns, minimize then maximize. Okay, where x1, x2 up to xm equal to 1 and all are non-negative. This you are simplifying in this manner. We are simplifying in this manner. Say this minimum of this first column, second column, third column, this minimum value, whatever is there, minimum value, let me say it is new. The expected minimum value, we are saying it is new. Okay, this once I'm saying minimum value is new. So what is say that minimum value is new? Minimum value is new means individually each of them that is greater than or equal to new. Minimum value is new. Minimum value is new means individually each of them that is greater than or equal to new. Okay, this is greater than or equal to new. So this new we are expressing in this manner. Summation over I varies from 1 to m, aij into xi, that is greater than or equal to new. And this is true for all the columns. There are n such column. So j varies from 1 to up to n. Okay, this. And what else here? There is some additional restriction. This x1, x2 up to xm, they are 1. And all these xj, they are non-negative. So this new, as you know, it may be positive, it may be negative, it may be 0 also. We do not know what is the expected value. So for some restriction here, if I am saying this new is positive, but when you solve problem, we have to make this new positive. So how do we achieve that? So we have to add some constant. So let me say the new is positive. If new is positive, there is no harm. So I can say mu is positive, that new is positive. So this new is positive, and we are going to, earlier I told, first take the minimum, then maximize. Minimum equal to new, that new we are going to maximize. Okay. So how to maximize this? So this new, okay, this new, this is the second problem. So this new, so we can express in this manner. So the new is less than or equal to summation over I varies from 1 to m, aij xi. Okay, this. So now to make the problem simplified in this manner. So the right hand side, as you know, the right hand side value is greater than or equal to new. So here this new, if you assume non-zero, it is positive, let me say it is positive, then you can divide the new both sides. So if you divide new both sides, right hand side will be 1. And so we are going to maximize new. So maximize new is equivalent to minimize 1 by new. So maximize new is equivalent to minimize 1 over new. Now, say what will happen to this? So this, once you are dividing by new, there is x1, x2 up to xn. You divide by new. See, these x1, x2 up to xn, their sum equal to 1. But once you are dividing, so that will become a different x. Let me say xi by new equal to capital X, capital Xi. So capital Xi. So and maximize 1 over new is same as minimize 1 of maximize new is same as minimize 1 over new. Okay, this problem so can be reformulated again in a different model. So now if you are talking about this Bayes problem, the Bayes problem minimize new. So this new you can say here minimize new is same as if the new is positive, minimize new is same as maximize 1 over new, and you divide by new and the problem you simplify. So as a result, you will have a linear programming problem. Now the same linear programming problem I am formulating in this manner. Say this is a problem, a linear programming problem, and what is happening to the player 1? So this has 3 strategy A1, A2, A3. So player B has 3 strategy B1, B2, B3. In this problem, the first row elements 2, 0, 0. Minimum is 2. Second row elements 0, 0, 4. Minimum is 4. The first row elements 2, 0, 0. Minimum is 0. Second row element 0, 0, 4. Minimum is 0. Third row element 0, 3, 0. Minimum is 0. So we are finding minimum is 0. And now we are talking about the maximum. First column 2, 0, 0. Maximum is 2. Second row 0, 0, 3. Maximum is 3. Third row 0, 4, 0. Maximum equal to 4. So 2, 3, 4. Among 3 maximum, we are finding minimum. So after taking the maximum, we are finding minimum. So see, max min value is 0 and minimax value is 2. So they are not same. So the game is a unstable game. There is no saddle point for this game. So now what is happening to this problem? You can see here. So we want to maximize Z for this first player. The problem is like this. The maximize Z, Z equal to new, and the new as you observe here, new is less than equal to 2x1, new is less than equal to 3x. So only one element is positive, rest two are 0. So only one element remain here. New is less than equal to 2x1, new is less than equal to 3x3, new is less than equal to 4x2. And what is happening to this x1, x2, x3? Their sum equal to 1. So in this problem, so the new is unknown. X1, x2, x3 is also unknown. See, there are three in equation and one equation. So I would like to utilize this. So as a result, and similarly, we find a Bayes problem like this. Minimize W, that is new, and new is greater than equal to 2y1, new is greater than equal to 4y3, new is greater than equal to 3y2. So, and their sum equal to 1. So, and this y1, y2, y3, they are non-negative. And here, this new is not the unrestricted in the sense because nothing is mentioned. But since this payoff matrix, the elements are positive, 0 or positive, so the value of the game has to be positive, cannot be. If the negative, positive, 0, the chance is that having the 0, but here it will be positive. So we can solve this problem. So if you solve, you can find here. So the optimal solution something like x1 equal to 6 by 13, x2 equal to 3 by 13, and x3 equal to 4 by 13. And if you sum, so 6 by 13 plus 3 by 13 plus 4 by 13, that is altogether coming as 1. And now we are interested to find the value of the game. So similarly, so we find the value of y1, y2, y3, 6 by 13, y equal to 4 by 13, and y2 equal to 4 by 13, y3 equal to 3 by 13, and the value of the game equal to 12 by 13. And the value of the game is, this is not the value of the game, this is the expected value of the game. The expected value of the game is becoming positive. positive means this is a gain for player A, not player B. So this problem, so if you are solving using the linear programming approach, say how to state this one. So we want to maximize new, so subject to this constraint. Okay, so this constraint, and you can say this summation over I varies from 1 to m xi by nu equal to 1 over nu. Okay, you are dividing by, so as a result you can write put capital Xi equal to xi by nu. So sum of all these capital Xi equal to 1 over nu. So our nu equal to 1 over summation over I varies from 1 to m, that is xi. So this problem is becoming like this. Maximize the objective function, that is summation over capital Xi. The small xi, their sum equal to 1, but this capital Xi sum is not equal to 1, subject to summation over I varies from 1 to m aij xi greater than or equal to 1. Okay, so or you can write this minimize summation over I varies from 1 to m xi aij into xi greater than or equal to 1, this, and xi is non-negative. And we have similarly wise problem. The wise problem is maximize this. So summation over j varies from 1 to n yj, summation over j varies from 1 to n aij into yj less than or equal to 1, and I varies from 1 to m. This y are non-negative. There are two problems. One, this problem is for the player A. The second problem is for the player B. So we apply the simplex method. So the first problem, you have to apply the dual simplex method, and for the second problem you have to apply the primal simplex method. So, and we solve the problem. Actually, if you find in a linear programming problem, the sum of the elements are negative. What do we do? So we add a positive constant. To make all these elements either 0 or positive. So, and once you are adding a constant, the value of the game is increased by that amount. If you are using k units, the value of the game is increased by that amount. So the expected value of the game also increased by that amount. And so if you are simplifying the problem, this present problem, so we have here like this. Say maximize y1, y2, y3, and these are the restriction, as you know. So we can solve this y1, y2, y3. This value, if you are solving the same problem, the value y1 is coming half, y2 equal to 1/3, and y3 equal to 1/4. But please note down, these are the capital Y1, capital Y2, capital Y3. They are not the probability of using strategy B1, B2, B3. So we have already changed. Say how we have changed. Now you sum it. Y1, Y2, Y3. You sum it. After summing this, you take the reciprocal. The nu equal to 1 over Y1, Y2, Y3. So that is becoming 12 by 13. Once this 12 by 13 is obtained, you can find small y1, small y2, small y3. Say how to find? So small y1 equal to capital Y1 into nu. Small y2 equal to capital Y2 into nu. And similarly, small y3 equal to capital Y3 into nu. So we have obtained the value of the small y1, small y2, small y3. These values are coming as 6 by 13, 4 by 13. So, and another is 3 by 13, 6 by 13, 4 by 13, 3 by 13. They are sum equal to 1. But this capital Y1, capital Y2, capital Y3, their sum is not equal to 1 because they are not the probability. So they are the probability into the value of the game. Okay. So if you divide the capital Y1, okay, so the small y1 equal to capital Y1 into nu. So multiply nu with the capital Y1, you will get the value of the small y1. Similarly, here also, so if you are calculating capital X1, capital X2, capital S3, so we are finding the capital X1 equal to half, capital X2 equal to 1/4, capital X equal to 1/3. So once the capital X1, capital X2, capital X3 are known, you can find small x1, small x2, small x3. Small x1 equal to 6/13, say small x2 equal to 3/13, and small x3 equal to 4/13. Okay, this. Is it all right? Hello?
Yes, sir.
See, I am solving another problem here. The problem is like this. Say, this is a pair of matrix. The elements are 2, -3, 4, -3, 4, -5, 4, -5, 6. Okay. So how this problem is formulated, just I am explaining little. So say there are 3 options for player A and 3 options for the player B. They are selecting some strategy, like say they are selecting 3 numbers, A1, sorry, 1, A2, 2, A3, 3. 3 numbers. And similarly, B1 is 1, B2, 2, B3, 3. So A is selecting a number, one of the number, say 1, 2, 3, he is selecting 1. Then B1 is selecting another number and they are adding. If after adding this number, if the sum is becoming even, then A gets that amount from B. If it is odd, then B gets that amount from A. So the 3 numbers, if you add, either sum will be even or odd. There are 2 options. So, and once he is getting the 2, say the sum is even, then B1 gets $2, let us say, from A gets $2 from B. If it is odd, then B gets that amount from A, either negative or positive. Okay. So here this the value 1, 2, 3 if you consider, and A1 is 1. So this is 2 -3, 4. 2 -3, 4. And second row, so that is A2 is 2, then -3, 4, -5. Then A3, that is 2, then 4, -5, 6. Say in the first row, there are 3 elements, 1 is negative. Second row, there are 3 elements, 2 are negative. Third row, 3 elements, 1 is negative. So we want to check whether this given matrix, pair of matrix, is stable or unstable. Stable or unstable. So stable or unstable, how to check? So row wise we find the minimum. First row minimum is 3. Second row minimum is -5. Third row minimum is -5. So -3, -5, -5. So maximum is -3. So we have got maximum equal to -3. And now what we do? Take the column wise maximum. So maximum equal to 4. Second column maximum is also 4. Third column maximum equal to 6. So among the maximum we find the minimum. Minimum is 4. So see, first we have taken minimum, then maximum. Max min is becoming say -3 and minimax is becoming 4. They are not equal. So the game is a unstable game. Now, I told if there is negative elements, if you find negative elements, some elements, some constant, we may add to all the elements. We are adding some constant. What is the constant we are adding? We are adding to this problem 6 to all the elements. And if you are adding 6, if you are adding 6 to this problem, so the value of the game or the expected value of the game is increased by that amount. By that amount, we are adding 6. So if you are adding 6, 2 is becoming 8, -3 is becoming 3, and 4 is becoming 10. And second row, the elements 3, 4 is becoming 10, 5 is becoming 1, and third row elements, the 4 is becoming 10, 5 is becoming -5 is becoming 1, and 6 is becoming 12. We have added 6 to all the elements. So if you add a constant to all the elements, the value of the game is increased by the expected value of the game is increased by that amount. So after adding this, we are formulating 2 linear programming problem for this problem. Say, what is the problem you can see here? So this problem we have 8, 3, 10, 3, 10, 1, 10, 1, 12. So with respect to this, we have introduced small x1, small x2, small x3. After that, we have divided by small x1 by nu, the value of the game, and we have formulated the problem. The linear programming problem here is becoming capital X1 or capital X2 plus capital X3 subject to 3 constants 8, 3, 10 greater than or equal to 1, 3, 10, 3x1 plus 10x2 plus x3 greater than or equal to 1, then 10x1 plus x2 plus 12x3 greater than or equal to 1. This. And what else is here? All these x1, x2, x3, they are non-negative. Similarly, we have another problem for player B, that is first player A, you are minimizing, and the player B, you are maximizing. So this is another problem. You can see here the y1 plus y2 plus y3 subject to 8 y1, 3 y2 plus 10 y3 less than or equal to 1, 3 y1 plus 10 y2 plus y3 less than or equal to 1, 10 y1 plus y2 plus 12 y3 less than or equal to 1. This. Now we are going to solve this problem. So here, to this first problem, you have to apply the dual simplex method. To the second problem, you apply the primal simplex method, because here the constants are greater than or equal type. You can also apply the big M method or two-phase simplex method. So here, generally, we solve one of the problem, either first problem or second problem. If are we applying the solving the second problem, we apply the primal simplex, first problem dual simplex, and we find solution. So the solution is like this here, and with respect to this, we have nu equal to 1 over y1 plus y2 plus y3. This is becoming 6. Okay, our nu is becoming 6, and once the nu has got 6, so we have here y1, y2, y3, y1, y2, y3. Now, say once these are the small y1, small y2, small y3. Okay. Once we are finding the small y1, small y2, small y3, so here we can find the capital Y1, capital Y2, capital Y3. So this is exactly, as you know, the nu equal to 6. So multiply. So our Y1 equal to capital Y1 equal to So capital Y1 by nu equal to 1 by, sorry, small y1 by nu equal to 1 by 4. Nu equal to 6. Once you got 6, you can find capital Y1, capital Y2, capital Y3. So the value of the game, so we got 6, and we have also added in a 6 to all the elements. The actual value of the game or expected value of the game is becoming 0. 6 minus k, we have added k equal to 6. So 6 minus k equal to 0. So we have got x1, x2, x3. They are also same value. It is a symmetric game, and this gives the answer. So this problem, what we have formulated. So many steps here are available. So whatever we have taken, if you say this nu is not restricted, unrestricted, okay, nu is unrestricted, so this nu will be free variables. So in our problem, we have used something like nu is restricted. We have added a constant, and after adding the constant, say the value of the game becoming positive, non-zero. So if positive, negative elements are there, the value of the game, for example, in some problem, the problem what you have taken here, it is 0. So this is 0, this value, the value of the game, presently it is 0. But once you have added this constant 6, the value of the game is increased by 6 unit. Okay, so here if it is 0, now we are adding, so 6, it is becoming 6. But how we have obtained, after solving the problem, we are finding the nu. Nu is the value of the game of the we have reduced. So reduced means we have added a constant. So the value of the game is increased. So that once the final value is obtained, we subtract again. After subtracting again, we find the actual value of the game. Actually, this problem, the actual value of the game equal to 0. Okay. So any doubt anywhere? Hello? This problem, what we have taken in the very beginning, I told the game is not a stable game. We like to solve it. Okay. So 2 by 2. This problem. This is an unstable game. We are interested to solve the problem. Okay. Now, so for this problem, say this is a unstable game. The elements are 2, -3, -3, 4. 2, -3, -3, 4. Okay. So please note down. Please note down here. So if you are using, so in this case, so this game is an unstable game. The probability that the first player is using his first strategy, that is x1, and probability of using the second strategy is x2. So with respect to this, we have, say, you can write down twice x1, Hello? Are you writing?
Yes, sir.
Hello. Twice x1 minus thrice x2. Twice x1 minus thrice x2. Okay. Twice x1 minus thrice x2 equal to new. Twice x1 minus thrice x2 equal to new. All right. Are you writing? Twice x1 minus thrice x2 equal to new. Then for the second column, minus thrice x1 plus 4x2 also equal to new. Okay. First column, twice x1 minus thrice x2 equal to new. Second column, minus thrice x1 plus 4x2 equal to new. So we like to simplify now. So if you simplify, so we have here 5x1, okay, equal to 7x2. 5x1 equal to 7x2. x1 plus x2 equal to 1. If x1 equal to x2 equal to 1, then we have x1 equal to how much you can write? So 5x1 plus 7x2, 5x1 equal to 7x2, and x1 plus x2 equal to 1. So as a result, we are finding x1 equal to how much?
Sir, 7 by 12.
X1 equal to 7 by, yes,
12.
7 by 12. And x2 equal to
5 by 12.
5 by 12. Okay. So if x1 equal to 7 by 12, x2 equal to 5 by 12, and what is the value of the game? Calculate. Because we have taken twice x1 minus thrice x2 equal to new. So then we have 14 by 12 minus 15 by 12
Sir, minus 1 by 12.
equal to new. So this is actually coming as how much? New equal to minus
1 by 12.
14 by 12 minus 15 by 12 minus how much?
1 by 12. Minus 1 by 12.
Minus 1 by 12. This, so this value, so it is coming negative. Negative means what? This value, whatever got the new, this is the expected value. This is the expected value. Okay. So please note down, if it is a 2 by 2 game, you can apply this rule and solve the game. So if it is 2 more than 2, so this may not be directly applicable. So you have to formulate the linear programming and solve. Okay. For 2 by 2, it is becoming simple. And since it is negative, this is the gain for player 2. Gain for player B negative. So instead of minus 1 by 12, if it is plus 1 by 12, it is gain for player A. So in the same manner, you can find y1 and y2. What is y1? How to calculate? So you can write down twice y1 minus thrice y2 equal to new. Then minus thrice y1 plus 4y2 equal to new. Now solve. So you will find again same value. What is our y1? Y1 will be
7 by 12.
7 by 12. And y2 will be
5 by 12.
5 by 12. This is because the game is symmetric. This is a symmetry game. For the symmetry game, so you have symmetric answer. So for a symmetry game, we have symmetric answer. So the value of the games is also becoming minus 1 by 12. Now, this is not a stable game, it is an unstable game. For the unstable game, we have to use probability, we have to use mixed strategy to find the expected value of the game. Okay, that's all. Okay, so if you have any doubt, you can ask me, I will explain. This, the game theory, the last portion actually. So I do not know. So from which section, how many questions, but I'm thinking around say 5 questions. So 5 or 4, I think 5 is all right. Okay. So maybe it's like this. So game theory 1 question. Okay. Transportation 1 question. Assignment 1 question. Okay. Duality theory 1 question. Integer programming 1 question, like this. Is it all right? Or you don't want the game theory?
So like if we drop means don't want game theory, I didn't get so like you won't include the
See,
question.
I'm telling here, this, you know, for any problem, the problem is difficult in the sense framing objective type question is difficult. Okay, because you know you have to have some option. Okay, so this game theory certainly I'm going to include, you know, because you know otherwise it's incomplete. So I think 5 question is all right, isn't it?
So like 4 would be better, sir.
4 certainly it is better. Less, even 3 you can say 2 is also better. But let me say, so maximum 5 question. Okay, maximum 5 question. But my plan is like this. So duality theory 1, integer programming 1, so transportation 1, assignment say 1. So, and if you have already prepared nicely, certainly you will be able to do nice. Okay, so but try to solve yourself and provide the answer. But if you borrow from somewhere, so what he's writing, whether it's wrong or right, so difficult to judge. Okay, and the game theory certainly. So maybe 1 question. Okay, so see, I will tell you, say, the game theory. So the summary is like this. Once, so we are talking only about the 2-person zero-sum game. Okay, 2-person zero-sum game. For the 2-person zero-sum game, we are formulating payoff matrix. Okay, so if payoff matrix are formulated, what we are doing? We are checking whether the game is stable or unstable. If it is stable, we'll solve the game because the game has a saddle point and we'll find the value of the game. If game is unstable, so there is no saddle point. So we have to formulate, say, a linear programming model to solve the game. To solve the game means we are going to find the expected value of the game. Some probability distributions are used for the setup strategy. So we are finding something like x1, x2, xn or y1, y2, yn. Okay. So once, so the x1, x2, xn are obtained, you can also find the value of the game and expected value of the game. Okay. So in the game theory also, directly or indirectly, the linear programming is also involved. That is the reason this portion is included in the game theory. Okay, right? So this slide I think I have already given to you all. Hello?
No, sir.
Yes,
we
sir.
did
I found it
review.
in Teams.
I have not given?
Sir, in Teams it is available, sir.
Okay. So again, I will also upload, but I will talk to the person concerned. So after the date and time is fixed, I will inform you. But most likely, almost all the students you are appearing online. Yes or no? If anybody offline, you have to contact me. Okay. So I have to plan accordingly. Okay. So the maybe what the institute is deciding. So maybe some exam will be conducted somewhere in Nalanda. Okay. So, but most likely all are opting for online test. Yes or no? Because what the guidelines say that we have to consult, because they have some data. So we have to consult the students and take the decision. So if any students is saying no, I want online, offline, so he has to communicate, and he has to decide again. So, and the date and time will be intimated. Okay. Thank you. So I will stop here. Okay. Is all right?
Thank you, sir.
How many students were available today? Can you tell me?
So around 60.
Okay, fine. So please inform all. I will send mail today after deciding the date. So the very soon. Okay. So exam will be on. So tomorrow be also available. We like to discuss again. Okay, right? So whatever the time is available, so I would like to discuss the whatever you have covered. Okay, tomorrow I will not repeat again anything, but whatever you have covered, we will discuss from that. Okay, you can ask your doubt. Okay, right? But class will be there, but we'll revise maybe the assignment, maybe transportation, maybe another. Okay. Thank you very much.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.